In today's session, we will discuss CMOS dynamic electrical behavior. So what is the difference between steady state electrical behavior and dynamic electrical behavior? So in steady state electrical behavior, the CMOS behavior is described when the input and outputs are not changing, which means that the inputs and outputs are fixed to the state. So the input and the outputs are fixed state. So say this input to the CMOS is 0. So the output of the CMOS circuit is 1. So now at the input, 0 is the fixed state, low state. And at the output, high state is the fixed state. So in steady state, the behavior of the CMOS circuit is described when the inputs are to a fixed state inputs or outputs are fixed state. Whereas in CMOS dynamic electrical behavior, the inputs and outputs are not fixed here. So they are continuously changing here. And the behavior of the circuit is described under the continuous change of the input and outputs. And also the behavior of the circuit is described in CMOS dynamic behavior. In dynamic behavior, the CMOS behavior is described when the outputs are changed between the states here. When the outputs are changed between the states. Here, the difference between the steady state and the dynamic are, in steady state, the inputs and outputs are fixed to a state. And at that state, we will describe the behavior of the circuit. In dynamic behavior, the input and outputs are changing, and where the output is changes between the states. Under such conditions, the behavior of the circuit is described in dynamic electrical behavior. Dynamic electrical behavior. Now, what are the dynamic characteristics of the CMOS device? What are the dynamic characteristics of the CMOS device? Just a minute, just a second. So now what are the dynamic characteristics of CMOS device? So here the speed power consumption of a CMOS device, it depends on the dynamic characteristics and also its load here, the type of load which is connected to the CMOS output and also the dynamic characteristics. So based on these two, the speed and the power consumption of the CMOS devices depends. So now what are the dynamic characteristics now? So from this statement, the dynamic characteristics are the speed is one characteristic and the power consumption is another dynamic characteristic of the CMOS. And while we were discussing the introduction to the digital logic ICs or the logic families also, we were discussed the generalized digital characteristics of the ICs. So where we were also discussed the propagation delay and the power consumption are one of the desirable characteristics of the digital ICs. So here the speed, the power consumption of the CMOS devices, it depends on the dynamic characteristics of the device and also its type of the load. Here the dynamic characteristics are also called as the AC characteristics, as it refers to that output changes between the states here. Output changes between the states here. Between the states here. So now, what are the dynamic characteristics of the CMOS devices? The dynamic characteristics are speed and power consumption. Speed and power consumption. These two are the dynamic characteristics of the CMOS. So now, here the speed of the CMOS device again depends on the two characteristics here. The speed is one of the dynamic characteristic of the CMOS, and the speed of this CMOS device, it depends on the two characteristics. One is the transition time and the second characteristic is propagation delay. We have already seen the propagation delay in the generalized characteristics of the digital IC, but we didn't discuss this, the transition time. So here the speed of the CMOS device, again it depends on the two characteristics, the transition time and the propagation delay here. Now we will discuss the transition time and propagation delay. So the first one is the transition time. What is transition time here? What is transition time? The amount of time that the output of a logic circuit takes to change from one state to the another state is called the transition time. It is the amount of time that the output of logic circuit takes to change from one state to the another state. Or simply, the transition time, it can also be defined as, it is the time required to the output of a logic circuit to change from one state to the another state. Simply, the transition time is nothing but it is the time required to change of the state from one state to the another state. From one state to the another state. So now, so here the ideal transition time or the realistic and the actual transition times are shown in this figure here. So from this figure, you can see the ideal transition time and also the realistic transition time from the figure B, and from the figure C, you can see the actual transition time here. Actual transition time. So from the figure A, it shows that, or even one, we get from the figure A, we get that the output changes instantaneously here. And even one can also expect that the moment when we apply the input, we wanted to see the change of state at the output. Ideally, everyone can expect the kind of output. So the moment when you apply the input, instantaneously, there should be a change in the state of the output. So this is from the figure, it is the ideal characteristic, and in this the rate of change of the output state, it is instantaneously there. It is instantaneously there. But however, the real outputs cannot change instantaneously here. The real outputs cannot change instantaneously because they need time to charge the stray capacitances of the wiring connections, of the stray capacitance of the wire connections, and also the other devices that they drive here in the circuit. So because these two factors, the output cannot change instantaneously in the practical version. So if you see the figure B, so from the figure B, so the figure B is not quite accurate as of the figure A here. And here in the figure B, the output takes certain time. The output takes certain time to change from the 0 to 1. And the another possible different time to change the state from the 1 to 0. So there are two timings are there here. One is the time to change from 0 to 1 is the rise time. It is called the rise time. And another different possible time is the transition of the time from 1 to 0. It is called the fall time here. Rise time and fall time. So why the output cannot change instantaneously? Because in the practical version, So the output circuits, they have the stray capacitance. They experience the stray capacitance, and the stray capacitance is because of the connecting wires and as well as the other devices which are present in the circuit and which are driven by the output of the circuit. So because of that, they are not because of that the change of transitions are not occurring instantaneously here. So the figure B shows the somewhat a realistic view of the output version here. Realistic view of the output. In that, the rate of change of the output, it is not same as of the figure A here. In figure A, you have instant change. In figure B, it is the output is not changing instantaneously because it takes certain time, and the time is called the rise time, and the another time is called the fall time. So what is the rise time and what is the fall time here? The rise time, it is the time required to change the state from the low state to the high state. The time required to change the output from low state to the high state, it is called the rise time. And what is a fall time? The time required to change the output from the state 1 to 0, that is high state to the low state, it is called the fall time here. It is called fall time here. So now if you see where we can exactly define or where we can how we can measure exactly the rise time and fall time from the output of the CMOS circuit. So there are some difficulties to measure the rise time and the fall time, because ideally here instantaneous state of change is occurring, but realistic we are not able to getting the same instant change of state at the output. So to avoid these difficulties, the rise time and the fall times are measured at the boundaries of the logic levels here. We know what are the logic levels. So the logic levels are the voltage logic levels. We have 4 voltage logic levels: VOL, VOH, VIH, VIL. So now you can determine, you can measure the rise time and the fall time. You can measure the rise time and fall time of the transition of the state by the boundaries of the logic levels. So that's why here from the figure C, if you observe how you are measuring the rise time and the fall time here, have a look on the third diagram, figure C. So here the rise time is the difference between these two here. The rise time is the difference between these 2 points. What are these 2 points here? See, the VIL maximum, VIH minimum. And what about the fall time? Again, here also we have the difference between the VIH minus VIL maximum here. VIH minimum minus VIL maximum here. And also you can see in the beginning and end of the transition, there is a smooth curve here. There is a smooth curve which is not in the figure B here. So in a realistic version, we don't have such a kind of smooth beginning and smooth ending transitions. But in figure C is the actual timing. It is the actual transition timing that occurs at the output of the CMOS device. And these rising time and fall time transitions can be determined with respect to the voltages of these levels here. With respect to the voltages of these levels. Can anyone tell what is the VIH minimum and what is the VIL maximum values? Can anyone answer for this one? Do you copy my question? Can anyone give for a 5 volts of range, what are the values of the VIH minimum and VIL maximum? Can you answer in the chat box? So can you give the VIH minimum and VIL maximum values? So how to determine the VIH minimum and VIL maximum? 70% of the power supply VCD and 30% of the VDD. For a 5 volts of power supply, the VIH minimum is 3.5 volts and the VIL maximum is the 1.5 volts here. So they are two representing the logic 0 and logic 1 of a CMOS logic. So now if you know the time response of at these two values and the difference between these two can give us the rise time and fall time of the CMOS device here. So now, so for concluding for this slide, what is the transition time here? The transition time is defined as it is the time required the output of a logic circuit to takes or to change the state from one state to the another state is called the transition time. Is called the transition time here. So that is what we are saying here. The output takes certain time to call the rising time and the different time called the falling time. So here the rising time is the transition from the 0 to 1 and the falling time is the transition from the 1 to 0. From 1 to 0 here. And here the rise time and the fall times, the rise time and the fall times are, depend on the two factors here. They are depends on the two factors. One is on resistance of the transistor and the second is the load capacitance here. The speed of the CMOS, it depends on the two characteristics, transition time and propagation delay. And now we are discussing the transition time. The transition time is the time required to change this output state from one state to the another state is the transmission time. So in the transmission, we will have the two time periods called the rise time and the fall time. And the rise time can be defined as it is the time required by to change the output state from 0 to 1, and the fall time is defined as it is the time required by the output of the circuit to change the state from 1 to 0. Okay, and now the next point, the rise time and fall time of the CMOS output device. Now it depends on the two factors here. The two factors are, one is the on resistance of the transistor and the second one is the load capacitance here. And on resistance, it depends on the properties of the semiconductor material, whether it may be of N type of semiconductor or the P type of semiconductor. Depending on the semiconductor material, the transistor has a on resistance, right? Then the second one is the load capacitance here. So how we can model this load capacitance? As I said that the output cannot change instantaneously. Even if the input changes at the input, the output cannot change instantaneously at the output here. It is because of the load capacitance. It is because of the stray capacitance. So here the stray capacitance is called the capacitive load or the AC load here. The stray capacitance is called a capacitive load or the AC load. And how it can be modeled here? It can be modeled because of the three sources here. The stray capacitance is present in every circuit and it can be modeled from the three sources here. It can be modeled from the three sources. What are that? Output circuits, input circuits, and the wiring connections between the output and the input from one stage of output to the another stage of input. That also realizes as a stray capacitance because we use to connect the one state to the another state with the wires. And the between the two wires, one is the VCC and other one is, let's say, ground. So now the vice also models, or the vice also realizes the stray capacitance, and which is in the order of the 1 picofarad. Now, what about the output and input circuits? Let's say the output circuit. So when you have taken the CMOS inverter circuit, the output transistor models some stray capacitance, because it has a 3 terminals, source, gate and drain, and these terminals, across the terminals, it offers the or it models the capacitance. They will be viewed as the capacitors, and the capacitance is the stray capacitance. And also the internal wiring and the packaging also have the capacitance. So from this, so it models the stray capacitance here, and it is in the order of 2 to 10 picofarads. What about the input circuit? When an output is connected to the another stage input, and when the output is connected to the another stage of input, again in that stage also we will have transistors, and that transistor terminals also will model the stray capacitance here, and the internal wiring of those transistors and the packaging of that circuit will also realize the stray capacitance here. So the rise time and the fall time of the transmission time, it depends on the two factors: on transistor resistance, load capacitance here. On transistor capacitance is nothing but the N channel, P channel transistor on resistances. What about the load resistance? The load resistance, it is because of the connecting wires. It is because of the load, and it is because of the output transistors, or it is because of the input transistors of the next stage. These are all the sources. They models the stray capacitance, and this stray capacitance is called the capacitive load here. So now two factors, they affects the rise time and fall time of the transmission time. So now we will take the equivalent circuit for this, and we will analyze, and we will find the rise time and the fall times for these circuits here. So now take the equivalent circuit for analyzing the transmission time of the CMOS output. So for this, we are taking the CMOS inverter. So this one is the CMOS inverter. And the second part of the network you observe here, it is the equivalent load for the transmission time analysis. As we are very familiar with the CMOS inverter circuit. In pull up we will have the PMOS transistor, and in pull down we will have the NMOS transistor resistance. So that's why these two are replaced with the RP and RM. That's fine. And coming to this one, the equivalent load for the transition time analysis. Equivalent load for the transmission time analysis here. And here in this equivalent circuit, if you see, we are finding the three equivalent values here. One is RL, and the second one is the load resistance, load capacitance, and the load voltage here. And the load voltage here. Load voltage here. And here the RL and VN, the load voltage and the load resistances. So they represent the DC load here. They represents the DC load, while the CL, it represents the AC load here. So now the load itself, we have two types of the loads, DC load and AC load. What do you mean that of DC and AC? DC, if the output states are fixed to a state, if the output voltage is fixed to a state, I mean that if the output is fixed to a high state, or if the output is fixed to the low state. So if suppose if the output is fixed to the high